Yeah. We're live, right? It's very exciting. It's like the whole world is watching. All right, welcome back from lunch, everyone. We are really excited to start the lightning talk session. These are just rapid fire talks about many of the exciting things going on in the community. So kicking things off is Josh Fromm. Take it away, Josh.
Thank you. Hi, I'm Josh. I'm a student here at UW, a grad student, and I also work at OctoML recently. Today, I'm going to be talking to you a little bit about a project I did on creating fast end-to-end binarized networks. So a binary network is, a binary in this case refers to like heavy quantization down to 1, 2, or 3 bits. So we have a lot of the same challenges of quantization where you lose a lot of approximation or the quality of your data because we're using so few bits. But the upside is that you get to replace your floating point numbers with only 1 bit, which not only gives you compression, but also allows you to replace multiply accumulate with pop count x nor. So here's like a little visualization. You take your original data, which might be int32, you quantize it down to, in this case, 2 bits for activations and 1 bit weight, and then we get to do this pop count of 3 and 3. In this case, we're doing bitwise and pop counts of the other packed bit tensor. Now, this is already available in TVM. We have bit serial com2D and bit serial dense. They're able to give pretty good speedups on individual layers. So the key idea is we're replacing down to a single couple bits. We get huge compression and a promise of like 40x speedup because of the op count reduction offered by these XNOR pop counts. Of course, the hypothetical speedup doesn't translate to real life, and to get anywhere close to that, we have to leverage TVM very heavily. So the individual layers that we have today, bit serial com2D and bit serial dense, give you something like 8x to 12x speedup on that layer compared to floating point, which is also optimized with TVM. But one of the issues with binarization today is that everyone focuses just on the layer rather than the full model. And if you look at the other layers that are required to get a good implementation, you have things like scaling and pooling and batch norm and activation, and these typically are done in the floating point domain. And because the binary convolutions or binary dense layers are so optimized, they end up taking a big amount of time. So one of the things that we do in this paper, and I'm going to skip a little bit of the gory details, is but we introduce a quantized version of all these operations that requires only a shift and a scale. And essentially, it centers it around 0 and normalizes the range so that you get like powerful quantizations with very few bits. So we replace all this red with just the shift scale operation. There are a few nice things about this. Obviously, it's more efficient. We cut a lot of the ops out. But we also remove all high bit data types from the network. There's no floating point arithmetic. There's no int8 or int32 arithmetic. So it allows you to have like a truly binary end-to-end network. This can be really helpful on platforms like FPGA or ASIC, where you don't need a floating point ALU anymore. You just have your individual gates and counters for the low bit width operations. But even on CPU, we still get pretty significant speedups just by cutting out the chaff. So one of the other cool optimizations we can do with TVM is this bit pack fusion. So on small devices like Raspberry Pi or micro controllers like Logan will talk about soon, you're really limited by memory. And typically when we talk about memory, you think only of the parameter space, right? Like how many parameters do I have, and multiply that by the number of bytes per parameter. But when you're already compressing things with quantization or binarization, you also have to consider the activation space between layers. Like how much memory is it going to take to store the output of a layer? So in a typical quantization setup, you would, or even a binary setup, you the actual output of the layer is like int16. So you're kind of like, you come in with a small packed input, which is like single bits, and you expand out to int16. But then you're using all the space that you would require from int16, and you go right back down to binary. But by fusing the layers so that we pack directly within a tile, you can cut down the number of bytes used by a factor of 16. So this is like a huge memory saving that might be really valuable on microcontrollers, and also gives you some speed. So quick speedups. If we don't optimize our network, this is the unoptimized on the far left, we're actually like 6 times slower than a floating point network. But by applying all the TVM scheduling intrinsics, we get up to like 12x speedups. And there's a little ablation study over here that shows how each optimization has a pretty big factor. So the key things are by fusing our glue, which is things like batch norm, we get a 2x speed up. By doing this bit pack fusion, you get a 1.3x speed up. And without all of these optimizations, you would have a hard time justifying the loss of accuracy, which so that's what we said. These are some of our end-to-end speed ups. So we looked at both SqueezeNet, ResNet, or SqueezeNet, VGGNet, and AlexNet, and we get pretty compelling speed ups for 1, 2, and 3 bits. And we don't lose that much accuracy. The accuracy is also compelling, and we have some runtime measurements. So this will be available soon. Probably next month it'll be merged into TVM, and we'll have a library for training these low-bit networks as well. So hopefully that's in time. Thanks.
Excellent. Thank you so much, Josh. And because we're keeping things pretty rapid fire here, we don't have, unfortunately, enough time for questions for each talk, but please make sure to find the speakers throughout the rest of the day. So up next we have Siyuan talking about TensorCore and tensorization. Take it away.
Yeah. Hi, I'm Siyuan. So today my talk is about TensorCore and tensorization. I will talk about these 3 parts, and I will go to the first. What are tensor-cores? Tensor-cores is hardware accelerators in NVIDIA GPUs, such as Volta and Turing GPUs. And also, it provides some warp-level operation. A warp in GPU is 32 thread, and a warp-level operation means that we need to use the 32 thread totally to execute only one operator. So here is a short example of TensorCore programming. We need to create fragments and load fragments, then do the computation in the fragment, and then store the data, store the result from the fragment to the shared memory or global memory. So here is a summary of the TensorCore. TensorCores are hardware accelerators, and it provides warp-level operations. It is different from our traditional operator. And it provides a new memory scope called fragment. And we must need to use the fragment to call TensorCore operators. So let's talk about the TensorCore support in TVM. We need such 3 steps to use the TensorCore in TVM: memory scope, create schedule, and tensorization. Currently, we have such 3 memory scopes: global, shared, and local. To support the TensorCore, we must add 3 special memory scopes called WMMA, matrix A, matrix B, and accumulator, which corresponding to the name of the fragment. And in traditionally, we usually copy the data from global to shared and do some reuse in shared, then copy to local to do computation, and then store the result to the global. For here, we just use the fragment and local together to do the computation, and then output the result. After the memory scope, we need a new schedule called warp-level schedule. I provide an easy way here. Just make the block dimension x equal to the warp size, which is 32, so that we have a warp matrix organized by the block dimension y and block dimension z. And we can just bind the thread index x to any loops except it contains the warp-level operators. The last step is the tensorization. Just replace part of the low-level IR into one intrinsic. And we can use such intrinsic here, just call TVM MMA sync to call the TensorCore operators on the CUDA level. So here's a performance improvement over non-TensorCore in TVM. We can see that in all scenarios, we have about 5x speed up. It is a huge improvement. And also compare with the CUDA, we can have competitive performance on traditional workloads and some faster performance on the emergency workloads. And the batch mode is the most fastest workloads in our TensorCore TVM. And it is widely used in BERT so that we can make huge improvements on the BERT inference. So here's a short summary that we provide massive speed up over non-TensorCore TVM and competitive performance with CUDA and CUBLAS. And it is based on the tensor intrinsic. And about some future works, we will use the TensorCore Utopia relay to help users to use the TensorCore in their models. And also apply TensorCore to some popular models such as BERT, because we should do very fast on the BERT inference. Thank you.
Okay. All right, great work. So please go. Next up, we have Xiaoyong talking about automatic TensorCore scheduling.
Hi, my name is Xiaoyong again. So just as Siyuan talked about the TensorCore and Tensorize, we are seeing it's making the infrastructure work ready. Now we are seeing how to make it automatic, right? And reuse the existing CUDA optimization schedule. So basically, you see here, if you want to run the TensorCore and Tensorization, you need to go to write your own schedule, right? We are seeing that we try to generate the TensorCore automatically. Make reuse of the thread level kind of scheduler for CUDA coding. Basically, you have, well, in that situation, they have contained that you have web tile size has 60 by 60 by 16 for CUDA 9, and for CUDA 10 now you can support 32 by 8 by 16 and 8 by 32 by 16, right? And the way we are doing that, you will see our left side in the orange box, we have IR passes to transform subtrees to TensorCore intrinsics. Now, you can see we can use the same schedule for CUDA and TensorCore, but you have to add an attribute. I have to add. So the way we are doing it, we have 4 steps. Basically, first one, we have to do a pattern match. It's right in the IR transform. Then we have 3 stages. Then one is from load stage, one is execution stage, the other one is the store. So just as we have some memory scope from the shared or global memory scope, we can put into the local. That's the first one. And how we identify that this pattern is based on the store IR. After in the middle, we try to execute it. So we're still based on the IR. We see the CUDA core is generated. Basically, this CUDA will store into the local FP32, right? The input will be FP16 or integer 8. This kind of TensorCore supported, right? Then we cast it to the Mac in that. Afterward, you will see how we move the memory from the local memory to the global store memory. If we have these 3 patterns matched, okay, now this one is a good candidate. And also, we already marked this attribute as, okay, it's a TensorCore enabled. So, but even just as Siyuan talked, we have to identify metrics, either if matrix A or matrix B, or it's a row major or column major. What we are doing is we are trying to see, okay, we visit the computer OP, they retrieve the indices from input matrix. So the index 0, index 1. Now compare these indices to the acids and reduced acids in the computer OP. Now you have some lookup tables there. So index 0, index 1, K and M. You will say, okay, this one is matrix A, the other one is the column major, right? So with this one, you can automatically get this attribute out. The third thing that just as I said, every thread you have to, not like WAP. WAP, they have different WAP index, right? For here, so for MMA, the north star should be the same. So we are doing some thread index identification to make this WAP index go to calibrate to the thread index to 0, and we have a thread index Y0 so that we can make the TensorCore block. The final thing is that you create the MMA sync intrinsics. So for WAP, you have 32 threads. So their equation between each other is that you have a TensorCore block, you have a CUDA 32 WAP. So, and also they have 16 by 8 kind of different. So we have to make this equation work. So the way we are doing that in the IR, we find the interval to schedule according to the access DCs in the fragment registers. If you see the above that for loop, which already is 16 by 8, the 32 thread, right? In the analysis, we try to I think outer loop index go to by 16, the inner by 8, then you will try to replace that CUDA with the MMA sync. With all of this, you will generate that computing ready. So the other performance optimization, you will see, say, all the kind of CUDA already code is the same, so auto-tuning and vectorization, double buffer in the storage alignment. All of this can make reuse. But the one of the things we have a virtual thread to do data reuse. That one still available. So that's the performance gate I already talked about. So we are CS 1.2, and for compared with the CO plus, and also it will apply for V100 and integer T4 for different kind of data type in the TensorCore. We already have a tag block written in the TVM. Please check out. So that's all. Thank you.
Super cool. Yeah, okay. And thanks to the speakers for keeping things really rapid fire. This is perfect. We are right on schedule. Okay, up next, Yao telling us about dynamic model graph dispatcher.
Hello, everyone. I'm Yao from Amazon. So today I will talk a bit more about our ongoing work about to support dynamic model in TVM. So in this morning, Gerard and Hai-Chen has talked a bit about the dynamic model infrastructures, especially of how to, basically how we're gonna dispatch each kernels to generate code. And in this talk, let's think a bit more about the challenge in the dynamic code generations, especially some disadvantages for the kernel dispatching. Like if we dispatch each kernel in our graph, one obvious disadvantage is that there will be extra overhead. Like, because think about for example, for a CV model, we have, say, 50 COM2Ds, and we have to do 50 dispatching tree operations for each convolution. So that will become like significant overhead. And the second disadvantage is that think about the convolution optimizations in hardware devices like in x86 CPUs. We have to transform to another data layout format to get better performance. So for dynamic shape scenario, this will become very difficult to support if we want to dispatch like each convolution at runtime and decide which layout to use. This means that we have to keep track our layout transformation. We have to have a runtime like layout tracking system, like to track not only the layout for our COM2D, but for every operator. And we also need a generic like layout transformation like operator, which is very difficult to implement and optimize for our runtime. Like the third one is it will become very difficult to apply graph tuning, which gives us, which potentially will cause some performance loss. So to avoid these disadvantages, one work we propose is to use graph dispatching strategies instead of kernel one. So the idea is that instead of dispatch every kernel, we dispatch or copy the whole graph depending on the input shapes. For example, for ResNet, for the dynamic batch scenario, we dispatch the input data depending on for the different input batch size, and for each bucket of the batch size, we just copy ResNet, and then in this case we'll have like for example 8 ResNet copies, and thanks to the functional programming nature of relay, we can easily achieve this by sharing all the parameters, and the only thing we need to take care is how we build the dispatching tree. Like for the dispatching function, this is an example of how to support dynamic batch or even dynamic input images. Like for every input shape indexes, we split them into different buckets, and then we build an if-else block trees so that we can, like for every leaf node of this tree, we can have a copy of our original graphs. And for each graph, oh, you have a question? Oh, okay. So yeah, this is basically for every graph, we can do whatever we have already done for our static shape graph. Yeah. Thank you.
Excellent. Okay. And perfect. All right, up next we have Wuwei telling us about efficient quantized inference on CUDA with TVM.
Hello everyone, I'm Wuwei Lin from CMU. Today I'm going to talk about quantized inference on CUDA with TVM. I believe most of you got an idea why we need quantization. It is more efficient and it's also serve model size, so it's a general model optimization method, especially for inference. And this is an overview of quantization in TVM. We have two quantization modes. The first one is the automatic quantization pass in relay, which quantizes an existing floating point model, and it modifies the model, insert new operations, and perform calibration to find the best parameters and produce a quantized one in relay. The other one is QN dialect, which allows us to import quantized models from other deep learning framework to relay. So both approach produce quantized model in relay, and then we have a unified optimization for quantized model. First, we have relay level optimization, which performs some general graph optimization methods, such as layout transformation and operator fusion. And then in the tensor expression level, we implemented a set of quantized operators, such as quantized convolution and quantized dense operation. These optimizations are quantization specific and also target specific. Next, I'm going to show you how we optimize these operators in CUDA platform. The first thing we do is to utilize hardware intrinsic. As you know, currently many hardware support some very efficient intrinsic instructions, such as DP4A on NVIDIA GPU, which allows us to compute very efficient dot product between two AB integer vectors, and also TensorCore instructions, which are covered by previous talk. To use this intrinsic in TVM is very easy and straightforward. We declare the intrinsic as a tensor intrinsic, and then only we need in the schedule we only do a few lines of code to replace the original loop body with the intrinsic one. So this is the example of convolution. Another optimization is to use packet layout. Layout packet means to split and reorder the axis of the original tensor. So for example, in the convolution, we use NCSW4C and OISW404I for the data layout and weight layout. As this is the figure. So as you can see in the middle of the picture, for each position of the tensor, we actually get a group of elements, and then we compute the dot product using the tensor intrinsic. So this is very efficient. This is a joint optimization from both relay and tensor level. In relay, we run a pass to modify the layout of the original model, and then we implemented the operators in the new layouts. To use this layout is also to satisfy the requirements of the tensor intrinsic, and also to improve the memory locality. Finally, we optimize this operator with AutoTVM, which perform automatic machine learning guided optimizations for different workloads. And this is exactly how we achieve good performance for these operators. And here are benchmark on an NVIDIA GPU. We perform the benchmark for different workload and on different batch size. And as you can see, compared with floating point model, we achieve very competitive, significant speed up with quantization. We quantize the floating point to AB integers. And also compared with other framework like TensorRT, TVM has achieved very competitive performance, and it even perform very well on some emerging models. And you can check out this blog post for more information and a code for this benchmark. So here are a summary. We achieve very competitive performance with joint optimization from relay and tensor expression level. And we are also working on improving model coverage and calibration schemes. We recently released a full pipeline of data-aware calibration, which can improve the accuracy of the quantization. And finally, this is open source work, so we welcome your feedback and contributions. Thanks.
All right. And it's so nice to see folks using Relay to do all kinds of amazing things. You know, sometimes as a researcher you get paper rejections and things. It kind of gets you down. And we come to this event and it is extremely encouraging. So I just wanted to thank everybody for all the amazing work. Rounding out the lightning talks, we've got Logan, who's going to tell us about his work on micro TVM. Take it away, Logan.
All right, so this talk is going to be a bit of a whirlwind tour of what's been happening on the bare metal side of TVM. So we all know that TVM is great at optimizing models for its supported backends, but until recently, TVM hasn't supported microcontrollers because it's pretty difficult to interface with them. And so this is the problem that we've been working on for the past year. And so to solve this problem, we added a micro TVM backend that enables interaction with microcontrollers in a device-agnostic fashion. And so to be micro TVM compatible, you only need to have a GCC cross-compiler for the device and JTAG support. And so micro TVM makes use of these requirements by generating C code for kernels and then just using JTAG for device communication. And using this infrastructure, AutoTVM falls out naturally. And so you have the same runtime improved loop as usual, but it's just running through the micro TVM infrastructure. And in the context of microcontrollers, we load the kernels into RAM so we don't burn out the flash, hence we get faster iteration speeds. And so originally we were just going to show single operator performance, but just recently we got end-to-end models working. And so we grabbed this quantized CNN from one of ARM's embed tutorials, and we tried to evaluate micro TVM's end-to-end effectiveness on it. So we ran the evaluation on boards with ARM Cortex-M7 processors. And by using these boards with that particular network on the previous slide, we were able to compare against CMSysNN, which is ARM's library of ham-optimized kernels for their processors. And so I'm by no means a schedule hacker. So I threw together a standard convolution template, tuned it for about 5 hours, and got the results on the right. So you can see that CMSysNN is still about twice as fast. And that's because they're doing a lot of interesting tricks that we can maybe look into. But also because they're making heavy use of SIMD, which we don't emit vectorization intrinsics yet. So once we have better schedules, longer tuning runs, and vectorization support, I suspect we can close this gap. And so those were end-to-end results, and here are two convolutions that are found in that network. And they correspond to two distinct kernels in CMSysNN. So CMSysNN has better asymptotics. So on the left, you see the gap is a little bit larger because this convolution occurs in the middle of the network where the tensor sizes are a bit larger. But on the right, the tensor sizes aren't as large, so we're a little bit closer. So that's it for our current results, but there's plenty of future work beyond just low-level optimization. In particular, there's quite a bit that the host is still handling, even in this end-to-end execution. But now I think we're in a good stance to start whittling away at these dependencies and moving towards fully self-hosted runtimes. So as is the nature of lightning talks, this has been, I've skimmed over quite a few technical details, but we'll have a more in-depth write-up coming to the TVM blog soon. And before I wrap up, I'd like to acknowledge Tianchi for being a fantastic mentor for this project. I don't know if I'd have been able to do it without him. OctoML for allowing me to go full steam on micro TVM for the last 3 months, and Pratish Patel for collaborating on early prototypes of micro TVM. And I don't think we're doing questions, so ignore that slide. Thanks.
Great work, great work. Well, thanks very much to all of the lightning talks. Those were fantastic. Really enjoyed it. I think up next, Thierry is going to take over. So I will hand you off to him. But let's give one more round of applause for all the lightning talks. I was super impressed by that great work.
Is it in here? Oh yeah, perfect.
welcome Professor Ziru Zheng from Cornell University. And we're very lucky to have him present his work on HeteroCL. So HeteroCL is this very interesting compiler that borrows ideas from HighLevel and TVM, but applies it to targeting FPGAs. And they're doing this by generating HLS code. And actually, in a past life, Ziru founded AutoESL that was...
Microphone.
Oh, sorry. Yeah, thank you very much. Yeah, so sorry about that. Let's welcome Professor Ziru Zheng from Cornell. I was saying that he's going to present this very interesting compiler work called HeteroCL. It borrows concepts and ideas from HighLevel and TVM and applies them to targeting FPGAs, which are very challenging targets to generate code for. And this builds on top of HLS tools, which Ziru in a past life founded a startup called AutoESL that was acquired by Xilinx and led to their HLS compiler. So let's welcome Ziru for his talk.
Thank you very much, Thierry. You can hear me okay, right? From the back. All right, so yeah, I'm going to talk about something different, right? So, I'm going to talk about how we recently extend TVM to target FPGA, right, to build highly efficient special purpose accelerators. So this is actually joint work between Cornell and UCLA, led by Professor Jason Kong's group. Quite a few students contributed to this project. Actually, 3 of them are here in the audience today. Yixiang, Wuwei, and also Cody contributed to the project as well before he joined Amazon. Okay. All right, so just want to give you a quick overview of HeteroCL. This is actually, like Thierry mentioned, this is a TVM build project, right? So we actually took inspiration from TVM. What's that? Oh, sorry. Okay, yeah, I did not notice. Thanks, Liz. All right, so and again, HeteroCL is actually TVM based, but unlike TVM, right, so which is mostly focusing on programmable engines like CPU, GPU, CSPs, right, or like some program accelerators. So we are mostly focusing on building special purpose, highly specialized accelerators. Right, FPGA, of course, is okay. So one of the ideal substrate, right, for implementing these kind of accelerators. So we actually want to be flexible. We actually wanted to support both declarative, also imperative programming. And also, we want to generate really high-performance code, high-performance accelerators. So I'm going to talk about like how we map to some efficient spatial architectures. And also, like TVM, we want it to be portable, right? So, we want to decouple, so these algorithm specification from the important kind of hardware customizations. So for us, we define 3 kind of hardware customizations, right? Compute, data type, and memory, right? So what do we mean by that, right? So really, if you think about hardware acceleration, right? So you want to run many things in parallel, right? As many as possible, right? So that's where we do parallelization, we do pipelining, right? So that's what we call compute customization, right? Of course, in many cases, right? So within the same silicon area, you want to run even more things in parallel, right? So that's where you exploit data type optimization, right? So you want to run things at the right precision. You explore the trade-off between the right area or performance and accuracy, okay? So you can do low Bose integer or fixed point or custom floating point types, right? And of course, the challenge is with these many parallel engines running, right, concurrently, how do we feed them, right, so that they are not starving? So this is where, like in most cases, right, so for this kind of special purpose hardware acceleration, doing a general purpose, right, memory hierarchy will not be enough, right? So that's where we have to use, right? So in some cases, very specialized cache structure or like memory banking or streaming and data reuse. Okay? So this is what we call memory customization. So we're thinking about many different kind of customizations, right? So really to realize many of this, right? FPGA is a fantastic platform, right? This is just a picture of the FPGA used in AWS F1, right? This is not even the latest, right? It's on the FPGA. But you can see like we already have like 2 million logic cells or lookup tables, right? For those of you who are not familiar with FPGA, okay, so you can actually implement an 8-bit addition or 8-bit adder with roughly 8 lookup tables. Okay, so with 2 million lookup tables, you can probably imagine like how many adders, right, we can run in parallel. And the DSPs are basically hardened multipliers. And there are also like ton of so on-chip bandwidth, right? So with this embedded block RAMs, SRAMs. Okay, so really, we have fine-grained parallelism, right? We can implement extremely low bandwidth, right? applications, we can also, in many cases, benefit from high performance per watt. But of course, it's also well known that, FPGA is extremely hard to program, right? Although it's a sort of programmable logic, right? Some people are joking that, FPGA is something, a device that's, built by the hardware engineers and for the hardware engineers, right? Not so much for programmers. Okay. And right now, in most cases, people still program FPGA with Verilog, right, or VHDL, RTL, right? So which is extremely painful, right? So this is just a simple counter, right? So you have to, spend these many lines of code, right, to take care of the clock and reset and everything, right? It would be much nicer, right, if you can get away with something like that with a high-level programming language, right? Okay, which is in this case just a C code. So that's where we're actually seeing this the community is actually embracing high-level design entries, right? These days, right? So that's where we are seeing the increasing use of HLS, right? So we bought HLS from Xilinx right now. Arguably, is still one of the at least most popular tools for academia, right? I don't have access to the custom data from Xilinx and Intel, but we get access to Google Scholar, right? If you just type HLS, we are seeing this right, nice steady increase, right, in terms of the use of the tool, right? At least for academic research project, right? So which is really nice, right? It's really nice to see that there are like even more than 3,000 papers, right, published since the tool, right, got right, so released. But on the other hand, right, so the reason that I want to show this curve is, so you see that this is a very nice increase, but this is sort of like linear increase, right? So how do we enable non-linear or super linear increase, right? So that's really the challenge. Okay. So with HLS, if you look at some of the again, I'm using VHS as an example here, right? So actually, HLS is pretty powerful. We can actually use HLS to capture these common optimizations that I mentioned, right? So this is actually a simple example, right? So where we make use of the HLS pragmas, also special data types to capture these custom data types, memories, and also, of course, compute customizations, right? But the problem here is that, the moment this code is optimized, right? This is actually highly optimized code. It's really hard to tell, right, what's going on, right? So it's really hard to recognize what is exactly this code, right? Because all these optimizations are already entangled, right, as part of the algorithm specification. Okay, so in case you're familiar with VHS, you can probably recognize this is just a simple convolution, right? But these are the things that we have to do to get high performance, right? But of course, this challenge is not new to this community, right? It's not new to CPU, GPU computing, right? This is where like Halide, TVM were developed, right, to decouple the algorithm from the temporal schedule, right? So we actually took inspiration from Halide TVM, right? So we want to, hopefully replicate same success, right? So of Halide TVM for FPGA programming as well. So we really want to cleanly decouple, right? So algorithm specification from these hardware optimizations, right? Not just the sort of compute customization, not just a temporal schedule like loop tiling, right? Interchange or like unrolling. We want to go even further, right, by decoupling data type and also memory customizations. Okay, so just want to give you some quick example, right? Of course, we are leveraging all the nice, awesome features, right, language features from TVM. So we also support deep character programming. So Heterosis is based on TVM, right? We naturally support, right? So these decoupled compute customization, like loop unrolling, piloting. Of course, in some cases, right, the way we handle that for FPGA is somewhat different from the way we handle that for CPU and GPU, right? But this is not new, right? But we are just leveraging TVM. So what we add on top of TVM is we are adding support for arbitrary precision, arbitrary build with integer. Okay, so because for hardware, like every single bit count, right? That means right you can save area, can optimize for timing, right? So that's where we add additional primitives, right? So we can resize integer or we can quantize a floating point into like fixed point. So it's downsize and quantize integers. So this is where we can really let the user to exploit this nice trade-off, right, between the performance and area and also accuracy, right? Right now we support arbitrary precision integer, arbitrary precision fixed point. We are adding support for floating point as well. Okay, so like for example, B-flow and BrainFlow is one of the things that we wanna target, right? So with this interface, actually much nicer to use than the, of course, right, the HLS, C plus HLS also allow you to do that through templated functions, but there you have to like do the recompilation, right, rebuild, right, to re-export this. Okay, so this is for data type customization. So we are also decoupling, like I mentioned, the memory customization, right? So if you look at it as a convolution, right, kernel, we have this window, right, 3 by 3, 5 by 5 window, right, moving along this grid, right, image grid. So really here, you want to build a specialized accelerator, you really don't need a general purpose cache, right? So this is where you can exploit the the data access pattern, right? So in our case, right, for FPGA, so in this case, if a 3 by 3 kernel, we only need to store 2 lines, right? This is so-called a line buffer, okay? With HeteroCL, we introduce something called reuse at. So where we say we reuse at along, in this case, a y dimension, so that the tool is going to automatically infer the data reuse pattern. And it's going to look at the data access pattern to generate this on-chip SRAM-based line buffer. Okay, and we can go further. So we can also specify we want to do reuse at along the x dimension. Okay, so that's where we can generate additional buffer like window buffer, which is actually based on flip-flops. So this will give us the full access to the the on-chip memory bandwidth. Okay, so with this, right? So that's where we can generate fairly high high performance, high throughput design. Okay, and all of these are on chip, right? These are memory storage are on chip. So we are also looking at how to handle the data placement, right? So when we have to deal with the off-chip communication as well. So this is a fairly new development, so that we are doing. Okay, so again, if you look at FPGAs, right? So FPGA is not homogeneous anymore, definitely, right? We have DSPs, right? Now we also have embedded CPUs, right? We are even seeing embedded AI engines and even GPUs, right? So like how do you measure this kind of data movement, right? So within the FPGA, right? Within the FPGA, there's something called CPU, or there's something called host outside the FPGA. Okay, so what we are doing is we are trying to come up with, again, extend the TVM to come up with a nice interface to specify where we do the data placement, where the data get placed, right? So in this case, assuming that, right, so we have a host, right, CPU, and then that can be specified by a platform description, and FPGA-based accelerator, by default, everything is stored right only on CPU. So we introduced a .2 primitive, right, sort of similar to some of the framework, deep learning framework you're familiar with, right? So that's where we move the data to the FPGA, and the compute, right, where we do the compute gets automatically inferred. Okay, so this is fairly natural, right? So of course we need to generate the right streaming, also on-chip buffers to handle this. Okay, but the nice thing about this is we can actually make use of this interface to specify the data movement within the modules on the same chip as well. Okay, in this case, if you have 2 convolution engines right on the FPGA chip, you can specify what if we don't want to do, right? So we want to also do the streaming across, right? So these are two sub-blocks. So again, we can just do another .2. So that's where we can enable the full streaming, right, between multiple modules on the same chip. So really, this is we think this is a really nice unified interface for us to specify this kind of data movement and also data placement, off-chip and also on-chip. Okay, so right now, we support quite a few different primitives, right? So like for compute, memory, and data type customizations. Okay, many of those are, right? So we are just leveraging the nice TVM infrastructure. Okay, but of course, right, in many cases, to really build a high-performance design, you have to use a combination of this, right, to get high throughput to really minimize also the area overhead. So that's where we are also introducing not just the micro primitives, also introduce some macros where we can map to very efficient, spatial architectures like system arrays, like stencils. Okay, I just want to give you 2 quick examples of this, 2 macros. One is we are leveraging the backend compiler from Professor Jensen Kong's group at UCLA. So where we can generate very high performance pipelined stencil architectures. Okay, so for those of you who are not familiar with tensor, basically it's just basically a sort of a window or like a fixed pattern that moves along the grid of tensor, right? So in this case, we can actually generate, again, this is application specific, highly specialized, right? We have this on-chip reuse buffers. So with this backend, we guarantee to have the highest pipeline rate and without banking conflicts and with a minimum on-chip data buffers. And also, there's another backend that we leverage called PolySA, also from Professor Jensen Kong's group, okay, where we can generate, application-specific 6-star arrays. So this is actually what can be generated from the tool. So this is actually for one convolution layer. You can see that there are actually so many different kind of, not just the standard TPU like star array for major multiply. You can actually generate many different kinds of star array with different kind of area performance trade-offs. Okay, so the tool actually allows you to explore this trade-off and then automatically choose some of this, right, based on the performance and area target. Okay, and also we are adding a mini DSL on top of TVM to support imperative programming. We cannot, unfortunately, synthesize regular Python code. That's just way too flexible. Okay, we cannot even define a synthesizer subset. So that's where we are adding, this fairly lightweight imperative DSL. So in case we have to, make use of some of the for loops, even else, right, to specify the algorithm where the, declarative programming is not sufficient. Okay, this actually allows us to support applications beyond just the deep neural nets. Okay, so these are the sort of this is the framework. This is the compilation framework that we have right now. Okay, so we are starting from HCL. We lower to Halide IR, and we go through some of the backends, right, that I mentioned, like the SODA with a stencil, and also PolySA for polyhedron, right? So polyhedron analysis-based C-solid generator. We are also leveraging the commercial HLS2 as well, like we got HLS for Xilinx, and Intel has HL2 as well. C-based, also OpenCL-based. We are also using, we can also target the compiler called Merlin from a startup company, this Falcon Computing. So the one of the nice thing about the Merlin compiler is it actually allows you to just specify just a few pragmas, right? Like when parallelize things, and it actually automatically handles many of the optimizations, like the unrolling pipelining and like array partitioning. Okay, so that's one of the very nice features. We are also extending the backend to support like near memory compute as well. Okay, so just want to show you some quick results. Okay, so HighLevel is still a fairly new project, right? Right now, we are looking at different kind of kernels, right? So like I mentioned, we don't want to just support deep neural nets. So of course, right? So deep neural net is one of the natural target, right? So but we can also support image processing applications, right? So with the stencil backend, also we can even support some of the bioinformatics, right? Application like Smith-Morderman. So we can actually get pretty nice range. We can support pretty nice range of applications kernels, and we can get pretty decent speed up on this AWS F1, right? Immediately. So in most cases, right? So the speed up is limited by the off-chip memory bandwidth between the DRAM and FPGA. Okay. And we're actually comparing with the optimized CPU and in some case GPU kernels, CPU kernels. Another perhaps more interesting case study is I actually teach FPGA also HighLevel synthesis course at Cornell. In the most recent offering, I had 34 graduate and senior students involved. These are actually very bright students. Okay. So one of the labs, I actually teach them without HLS, right? Teach them HLS. So one of the labs I asked them to do is to implement a simplified binarized neural net, okay, a BNN, on this Xilinx Zinc chip, right? So their goal is to implement, right? So offload the neural net to the FPGA and to get high speed up, right, over CPU, right? The higher the speed up they can get, right, the higher the grade they're going to get, right, for this specific lab, right? So that's the challenge, right? Okay, and they were given 2 weeks, right? And here's the histogram of the speed up, right? Good news is that most students can get some non-true speed up, right? So in some case 5x, some case 10x, right? But not so encouraging news is only 2 students, right? Out of these 34 students, they got this ideal speed up, basically above 50x. Okay. Of course, these are very busy students, right? They only got 2 weeks, right? And not, you know how this works, right? So usually the student only spend a few hours, right? Right before deadline. But we actually look at the sort of the winning entry from these 2 students. This is one of the examples, right? So indeed, right, it's actually non-trivial to get the speed up, right? So even with HLS, right, you have to implement this, important different kind of compute and also data type memory classification techniques. You have to this is a binary neural net. You have to do the bit packing, right? You have to reorder things, right? Do the tiling. You also need to bank the memory. You also need to do the line buffers, right? So this is definitely non-trivial. So that's why not everyone can get this high speed up. Okay, and later on, right? So, we also have a course project, right? Later on, a group of students, right? So who had the audacity to try out a fairly early version of HCL. So they actually re-implement this whole BNN using HCL. So within 3 days, of course, this is not fair comparison. They already got familiar with the BNN, right? They know what kind of optimization they want to implement. But with HCL, right? This is sort of a constant limit. They actually got 63x speed up, right? Which is a fairly encouraging sign. Okay. All right. So this is this also related. Okay, I want to just take a few more minutes to talk about another related work, right? So which is a collaboration between Cornell and also multiple universities with Intel labs, right? So led by Dr. Hongbo-Rong's team. So this is called T2S, temporal to, T2M means temporal to spatial. This is also inspired by HighLevel and TVM-like approach. So where we try to go even beyond, right? So we try to further add additional spatial optimizations, right, in this decoupled specification. Okay, we actually plan to use T2S as the backend for HydraCL, so that's why I'm bringing this up, right? So if you look at what we are trying to do is T2S is actually another DSL. This is actually built on top of HighLevel. So where we decouple the algorithm with this so-called spatial mapping. Okay, so to build very high performance application-specific arrays. Okay, so in this case, right, I'm not going to bore you with the syntax of the these primitives, but really this allows us to specify the data forwarding, network, the scattering, and buffering, right, explicitly. Okay, which turns out to be very useful. Okay, and we actually have pretty encouraging results. So this is targeting Intel, of course, right? So we compare with the OpenCL. This is for GEM, the GEM kernel, the matrix multiply. We compare with the GEM kernel released by Intel, the OpenCL compiler. So that's our baseline, right? That's like 70 lines of code. We also compare with Ninja design, which is created by expert, okay, who spent 18 months just optimizing this kernel to get the highest performance, right? To get the sort of peak performance on this specific Intel Air 10 FPGA. So with T2S, we only need 20 lines of code, okay, so to specify the algorithm, also spatial mapping to create this array. And you can see the performance, in terms of performance, we close pretty much 90% of the performance gap. Okay? So one of the common concern of HLS is like whether you can approach, right? So RTL design-like performance or not. So we believe that with HydraCL with T2S, we're gonna get there, okay, in a productive way. Of course, this is just a gem, right? We can also support, some of the more complex tensors as well. Like we are able to support like tensor decomposition, some of the common, and also get very high performance on the FPGA. Okay, so with that, I want to just quickly conclude, right? So again, HydraCL is a TVM-based project. It's fairly new, right? So we want it to be efficient, flexible, and also portable. Okay. So we are working on a few very exciting directions, at least to me. Okay. So like I mentioned, we are supporting this data streaming, right, both on-chip and off-chip, so that we can compose multiple blocks together, so to handle more than just kernels, so we can handle very complex applications. We are also looking at how to make use of ML, right, to do the design space exploration, okay, automatically. So this is definitely very challenging for FPGA because there are many more knobs that you have to turn. But we believe that there's actually some nice way that we can handle this. We are also looking at near memory sparse compute as well. So that's where sparse is already mentioned, right? So in quite a few earlier talks, right? So we actually believe that we need to code. We have a nice. There's actually a nice opportunity where we co-design the hardware accelerator. We can co-design the sparse storage format to get the highest possible performance. Okay. So yeah, at the end, just want to thank the TVM community, right, for the awesome work, right? So otherwise, this work, HydraCL, will not be possible, and also some of the sponsors, right, for this project. Again, HydraCL is fairly young, fairly new, but the alpha release are already up there on GitHub, right? So it's we released it a few months ago. Okay, so feel free to try it out. Hopefully later on, once we get right, so once this project becomes mature enough, we can handle right even more applications, right? So we'll be able to show that indeed, right? So we can enable similar success, right? So similar to TVM, we can enable more programmers to make use of FPGA, okay, in a much more productive way. All right. So with that, I'm done. Thanks.
Questions from the audience? So I guess I'm going to go ahead and ask a question. Could you share more information about your automation efforts? So TVM has AutoTVM, but you can get execution metrics very quickly because you're just programming a CPU or a GPU. When you're exploring different FPGA designs, to close the loop, you have to wait for compilation. So are there ways to shorten this wait time?
Right. So that's a super good question. So so on one hand, right? So FPGA gives you a lot more knobs, right? So in terms of the different kind of memories, right? So the on-chip memory that you can create, also in terms of how it pipeline or how it parallelize. But on the other hand, right? So in many cases, you actually want to shoot for the highest possible performance, right? You want to max out for the on-chip, right? The resource you want to get the highest pipeline rate. So there, to some extent, okay, we are facing more knobs, but at the same time, in some cases we can argue that it's more constrained, right? So for example, you want to get the basically fully pipeline design. So that's where we basically have to unroll pipeline and tell certain loops, certain loop nets, right? So that's sort of why I feel like there's actually a shot, right, at the automation.
Great. Okay. Other questions from the audience? All right, I have one more. Do you have any plans to target ASICs using HLS compilers like Catapult HLS?
Yeah, so that's also on our to-do list, right? Although right now the priority is not as high as the IPG support, right? But yeah, actually, some of we already got quite a bit of interest from different companies, right, from industry, right? Some of them have already expressed interest in terms of collaborating, right, for hypercell and targeting ASIC. So we'll see. It's not near term, definitely, but it's definitely possible.
All right.
Okay.
Well, let's. We have one question.
Yeah, I have one question. Okay. If I understand you correct, you allow the user to move data between different memories, but is it so that the user has still to define the memories himself, or do you interfere yourself a memory hierarchy? For instance, guessing which is the optimal cache size for a systolic array or similar.
Right. So basically, what we allow user to do is we allow user to specify, how to place data, right, in which module, right, and we are going to automatically infer some of the channels, right, the communication channels, right, between this module, also the buffers, right. Of course, there's a trade-off, right. So like, what's the buffer size and such, right. So right now, most likely we're going to rely on simple heuristic, right, for the short term. But that's why I mentioned like DSE, right, the automatic design specification, right, where we can explore, right, more design points, right, down the road.
All right. One last question.
I think this is very simple questions. Actually, I thought I personally ask you guys, but I feel I have time. So before a few months ago, I checked this project because I noticed we have the presentation today. So that project seemed pretty nice, but I felt that using the TVM used in this project seems a bit old. Do you have any plan to update that?
Sorry, so I missed the last part of the question. You're talking about status, right? You're talking about the status of the code base?
The version of TVM used in Heterosis.
Oh, yeah, right. So right now we are not using the latest TVM for sure, right? So we basically fork from TVM a year ago, roughly, right? Yeah, we do plan to integrate some of the more recent features, right? Yeah, that'll be pretty useful.
All right. Well, that's it for the questions. Let's thank once again Professor Zhang. Thank you.
Okay. Awesome.
Thank you. All right, next up, we're very excited to have John and Mingjia from Microsoft, and they're going to share their experiences on using TVM for serving models in the Azure cloud in production. So we're very excited to hear about this.
Hi, everyone. Thanks so much for coming. My name is John Seufer, and with me is Mingjia Zhang. We're from Microsoft AI and Research, and today we're going to talk about deep learning and TVM at Microsoft. Those are our handles on the forums and on GitHub. I regrettably chose a different one for the forums than my GitHub. but that's okay. So deep learning has permeated Microsoft products and services. It's used all over the company. For example, in Bing Web Search, we currently use deep learning to move from strict keyword matching to semantic similarity. This allows us to surface better URLs that better match the user's intent. And these same kinds of techniques are used in Bing features like entity search and conversational search. And it's even used in features like Bing question and answering, which is a pretty advanced feature where we can scan a web page and extract an exact passage from the web page that directly answers a user's question. Similar types of techniques are employed in Office products. For example, in Word, these same kinds of things do grammar checking, sentence rewriting. So these systems, though, are massively scaled. They're huge, large-scale distributed systems that may often run several models for a single query. And given the computational complexity of a lot of these models, the traditional solution of running these models in the same process as the other services doesn't really scale. This is why we introduced what we call the aptly named Deep Learning Inference Service, which serves models for Bing, Office, and Cortana. Currently, we serve millions of model inferences per second across hundreds of models and tens of thousands of servers in over 40 data centers worldwide. And one of the key design components of the Deep Learning Inference Service is that we want to promote data scientist agility. So data scientists all come in with their own favorite frameworks, their own requirements. So we support popular frameworks such as TensorFlow and PyTorch. We run models on both Windows and Linux, and models across CPU and GPU, and this is all running on Azure. And because Deep Learning Inference Service is being called from a lot of very high-scale platforms, we have really strict latency requirements, and this often means single-digit milliseconds. So to motivate why we need good, effective model optimization, we recently published a blog post about how we shipped a BERT model for Bing web ranking. This model alone gets around 1 million queries per second, and the TensorFlow latency out of the box was prohibitive for shipping this model. The latency and throughput were unacceptable, and the cost would have been way too large. So we took the time to hand optimize this model on an NVIDIA V100 GPU. We ended up getting an enormous throughput increase, and it moved this model from an unshippable state to a shippable state. We ended up saving millions of dollars in the process. The catch was it took over a month of dev time. And given the number of customers that our service serves, it doesn't really make sense to spend the time to hand optimize all of these models. So there were a bunch of learnings from that experience. The first one being most existing deep learning frameworks don't fit our requirements. And most of our requirements are, one, reducing latency to a scenario acceptable number. Most of you guys are very familiar with this. Supporting advanced models at large scale while still saving cost, and the agility to bring new optimization techniques from research into production. The model optimization can't take 1 month per model. That doesn't make a lot of sense. So we need to come up with some new and creative solutions to ship these models. So over the last couple of years, we've developed a handful of solutions that we've tried out. The first one is similar to what I just described, where we do custom optimizations. We either hand rewrite the model in C++ or CUDA. Internally, we have libraries named Deep CPU and Deep GPU. Sometimes we'll recreate the entire graph on TensorRT. And this has the obvious benefit of having really low latency and high throughput. It also has the best utilization of hardware because we're hand tuning everything. And the problem is that it has really low agility. Like I just mentioned, it takes a long time to run one model. The next solution is to lift some of these core components that we had handwritten and plug them into an existing framework. For example, you can lift an RNN that's handwritten, wrap it in a TensorFlow custom operator, and plug that directly into TensorFlow. And while that has the benefit of having some pretty good latency because you're still relying on these handwritten operators, it has suboptimal performance because the rest of the operators are still running in the native framework. So these two solutions spurred us to look at a compiler-based solution like TVM, where we can get benefits of graph-level optimizations, optimized code generation that runs cross-platform and cross-device. So the core question that we're trying to answer is, can we achieve low latency, high throughput, and high agility? And while TVM hasn't been the answer to all of these questions yet, we've had a number of successes with it, which have been really exciting. And next, I'm going to hand it over to Minjia, who's going to talk about some more of those successes.
All right, thank you, John, for the great introduction. And hello, everybody. I'm Minjia. So next, I will talk about our case studies on using TVM for model optimization. The first case study is a query understanding for bin. So this is a service where we encode the queries into high-dimensional semantic vectors and use for various downstream tasks. This model has like convolution neural networks and also LSTM with its type of recurrent neural network. And the latency target for this model is 35 milliseconds. With TensorFlow, we are getting more than 100 milliseconds for making to encode a single query on CPU. With TVM and some of our customized optimization, we were able to reduce the execution time to 34 milliseconds on CPU. And in particularly, like the approach we take here is a hybrid approach where we are plugging our deep CPU library into TVM as an external library. And as John just mentioned, the deep CPU is a highly efficient implementation for recurrent neural network on CPU. And since for this model, the LSTM contributes the large portion of the execution time for this model, we replace that with our customized ops. And in particular, we do this in 2 steps. And the first step we do a kind of graph matching. We automatically identify the subgraphs that correspond to the LSTM using the TensorFlow scopes. Then we do a graph rewriting, essentially replace the entire subgraph with a single node that corresponds to the custom ops supported by deep CPU. And with this optimization, we were able to reduce the iron part of the execution time from 63 milliseconds to 15 milliseconds. And then we count down TVM to do the optimization and auto-tuning of the rest of the graph, and that brings the latency of that part from 49 milliseconds to 19 milliseconds, which is a 2.5 times speed up. And more importantly, in this process, we have figured out that the TVM is really flexible in terms of adding external libraries and get the benefit of both like highly optimized ops as well as optimizing the rest of the graphs. The other case study is about Azure Q&A Maker service. So this is part of the Azure Cognitive Service used for creating question and answering bots. So behind this service is powered by a distilled BERT model. And the latency target for this model is 10 milliseconds. So with TensorFlow, it's 73 milliseconds on CPU and more than 10 milliseconds on GPU. So with TVM and some of our improvements, we were able to get 28 milliseconds on CPU and 5.5 milliseconds on GPU. So essentially making this model shippable. So more importantly, taking the example of running BERT on GPU. So in order to run TVM with BERT on GPU, we actually added a few ops that were specific to the BERT model, but were originally missing from the TVM. These are, for example, one-hot ERF activation functions, bad matrix multiplications with more than 3 dimensions. And with these ops added, we can run BERT entirely either on CPU or GPU. And next thing we found that is for BERT model, and especially in general for a lot of NLP models, there is a layer called vocabulary projection, which is usually implemented as softmax layer. And this layer can become really expensive as the vocabulary size grows. And vocabulary definitely is important for getting high accuracy for some of the NLP models. To mitigate this performance bottleneck, we actually implement a new softmax schedule, and we tailor specifically for vocabulary projection. And we auto-tune it on both CPU and GPU to get performance improvement. And with this, we were able to reduce the latency from this model from 9.8 milliseconds to 7.4 milliseconds. And we also looked into how to make TVM to better utilize some of the new hardware. For example, the NVIDIA V100 actually has TensorCore support. So these hardwares are super powerful. They're delivering like over 100 teraflops of computation throughput. However, it does require you, to get that kind of throughput, it does require you to do your weight, for example, weight computation in FP16. That's why we experimented and added, working on adding support for half precision and extended gem operations on TensorCore into TVM. And with some of our preliminary results, we were able to further bring down the latency from 7.4 milliseconds to 5.5 milliseconds. So at this point, compare this the TVM results with our hand-tuned version of BERT. I think there is still some gap. However, if you compare that with TensorFlow GPU, that already offers some quite decent speed up. More importantly, I think it makes it easier for us to, quicker to optimize further future BERT-like models with less or no extra cost. And we actually did look into some of the gaps between the TVM version of BERT and our hand-tuned version of BERT. I think the gap mostly comes from some of the fusion decisions, as well as data layout transformation, and as well as the register file usage. Essentially, hand-tuned version can do that in a more efficient way. But I think that opens interesting opportunities and next steps for us to look into to bridge that gap. So those were just two cases. We actually applied TVM to quite a few other models, and we are overall we're seeing TVM is quite helpful for improving the agility of model optimization, and we are actually contiguously adding contributing changes back to TVM. Some of the changes including we're adding new IR passes that are trying to expose more parallelism by combining independent dense matrix multiplications. And apart from adding ops coming from the TensorFlow front end, we're also adding ops that are from the Onyx front end, and more importantly, we are trying to add the Windows support for TVM and try to make it easier to use on the Windows platform. So overall, our experience with TVM is quite positive, and we think that it has vibrant and supportive and open community. It's very developer-friendly with really nice online document and very responsive forums. And it has quite encouraging in terms of innovating and experimenting with new techniques. And we have seen some really nice performance improvements over popular DL frameworks. And more importantly, we have been using TVM for shipping some of our models into production. So overall, we are super excited, and we are looking forward to contributing and trying out new features that are coming from the community. Thank you. That's our talk.
Thank you for the excellent talk. Are there any questions in the audience?
Hi, so just now you showed two case studies, both of them you have some customized optimization, like deep CPU, and the other thing is on GPU for BERT. So for those custom optimization, do you have any plan to open source them?
Correction, for the first case study, I think that's a hybrid approach where we use part of the ops that we leverage customized operations.
Right, yeah.
But for the second study, all our optimizations are done directly to TVM.
Okay.
So for the custom ops, libraries, we are actually working on open source it. But this usually takes some time as it involves the legal team. It's some process that needs to be going on. So we're working on that.
Okay, so you have a plan to open source them.
Right.
Great, thank you.
Okay, yeah.
This was awesome. Thank you for sharing. So have you explored using TVM for new hardware backends as well, or is it something that's without that? If you cannot comment, that's okay. I was just curious if there's anything.
That's interesting. We are definitely very interested in exploring TVM for new hardware, be it, for example, FPGA or other types of hardware. Yeah.
We haven't explored it too much.
But we haven't explored too much yet. Yeah.
Was there another question? All right, well, maybe one last question. There were some interesting findings from the Facebook group about use of sparse operations and block sparsity. Is that something that you've also investigated?
Definitely, yeah. That's something very interesting. Yeah. Actually, previously we did some optimizations regarding sparsity, but I think it would be interesting to see that how we can automate some of those optimizations and combine those with TVM. I think that'd be something very interesting to look into.
Yeah. And I think a lot of what we're moving toward is even more than just open sourcing some of our hand-tuned optimizations, is taking those learnings and trying to move them over into something like TVM so they can be applied more generally.
Yeah. All right, excellent. Well, let's thank the speakers once again.
All right, thank you.
Did you upload your slides or? Do I need to load them here? Pardon me? Do I need to load them here? We can use your
up, we're lucky to have Ramana come here and give a talk. He's a engineering lead at ARM and has been spearheading the adoption of TVM inside of ARM from the machine learning organization at and we'll be talking about their efforts. And I think ARM is a very interesting company where they have a lot of IPs in the form of CPUs, application class, microcontroller class, NPU-like devices, and GPUs. So it's going to be a very interesting talk. And Ramana came all the way from the UK, so let's thank him for coming all the way down to Seattle to give this talk.
Thank you. Thanks a lot for those very kind words. I'm Ramana Radhakrishnan. I lead the TVM team inside of ARM. I'm part of the machine learning organization, as Thierry said. And what I'm going to talk about today is essentially, I'm going to introduce a bit around what we see as the role of AI and ML in endpoints and the edge. I'll give a brief overview of ARM's ML platform, how we are using TVM inside of ARM, our current areas of interest and our future areas of interest, and challenges and observations of an ex-compiler engineer working on CPU compilers and looking at what this brave new world with TVM looks like. So what's AI being used for in endpoints? We see it being used for in endpoints for vision-style applications, which are images and video, voice for recognition and creation, and vibration analysis, and in terms of any signal. And we see that AI performs very well with patterns of data. We see also a diversity of AI requirements in the market. There's a lot of eager adoption of ML and AI for a lot of our customers. And we see a sort of differentiation in terms of the premium market, the cost-sensitive people, and people who are sort of somewhere in the middle. So what I'm going to be talking about today is a little bit around our ethos NPUs. A lot of talks today have talked about the ARM CPU and possibly touched a bit about our GPU. I'm going to introduce our ethos NPU, which sort of tries to bring the ML capability to every market segment. We've got three strands of that. We've got the ethos N77, which is sort of the high-end premium experience, which delivers best-in-class throughput and efficiency. We've got the ethos N57, which is sort of the best blend, middle-of-the-road kind of a thing. And we've got the ethos N37, which is sort of the lower-end, cost-sensitive design. After that sort of advertisement, what does our ethos NPU software stack sort of look like? We view this as we've got this working in terms of our existing software stacks. We've got the ARM-NN software stack, part of the ML platform. And we sort of see the ML application on the top connected to an ML framework. And we sort of look at TVM as an ahead-of-time option for us in terms of compilation and in terms of providing an ahead-of-time compiler experience for our customers. We also have the ARM-NN and machine learning platform, which also integrates down into the NPU compiler and driver. This is sort of talking in terms of the host Cortex-A CPU or the applications processor, which runs rich operating systems. We've also connected that to an ethos NPU, which has an MCE, a PLE, a network control unit, DMA, a DRAM. It's a fixed function accelerator. We've also got a software stack, which ARM, as you know, is part of a wider ecosystem. We've got our partners. We've got an ML platform that has a number of software products which support a number of the ML frameworks. A lot of those are around software libraries, which is sort of following the traditional route of deploying on ML, which is using things like ARM-NN, ARM Compute Library, and CMSysNN. Logan touched a little bit on CMSysNN during his talk earlier. And finally, at the lowest level, we've got a wide variety of IP that we are interested in terms of deploying to. You've got the Cortex brand of CPUs, which are really our applications processors for the client space. You've got Dynamic, which is really our big little solution. And you've got the Neoverse solution, which is targeted towards infrastructure and enterprise. We've also got GPUs for based on the Mali GPU. And we've got the NPU, which I'm introducing today around the Ethos brand. We've also got a wide variety of partner brand, and it's very nice to see a large number of our partners over here who target DSPs, FPGAs, and other accelerators of their own. So what are we looking to do with TVM for initially as part of my group? We are looking to do an ahead-of-time compilation stack with TVM. We are working on a graph partitioning at the relay level, where we are quite excited by the framework agnosticism and the number of different framework front ends that TVM provides. And we try and do a graph partitioning for our NPU at this higher level, and we try and offload as much as we can to our fixed function accelerator. We then go through the rest of the TVM stack, and we provide an annotated output. Similarly, as I pointed out earlier, the software stack has a runtime component to it. When we come around to to executing this on our IP, we would be able to offload the necessary bits by making the modifications to the runtime and running that on our NPU and our CPUs. So our current areas of work with TVM, I'm sort of listing a whole load of things that we are interested in and that we've been working on currently. We've done some support for Mali Bifrost in TVM. I'm happy to report that on some of the standard models, we were seeing improvements between 20 and 70%. The original Mali schedules that were in TVM were written for an older architecture called the Midgard architecture. They weren't really supported for the newer architecture called the Bifrost architecture. We used AutoTVM and wrote those schedules and provided them back to the community. They're in there. We're interested in improving the ARM CPU architecture support. As you well know, there are a number of instructions, especially in the Neon instruction space, which are not necessarily vectorized by either LLVM or GCC, but those could be used from the TVM's vectorizer module to get better performance, especially for quantized integer support. We're also currently investigating integrating our ARM compute library, which is essentially a set of routines that are highly optimized for our CPUs and our GPUs. We are investigating how best we could integrate that into TVM. We find the features of TVM where you have the ability to integrate with external libraries to be very interesting in that area. And that way, we are able to reuse some of the great work that's happened in our teams already. Other general areas that we've been working on recently is Ina from our team and Tristan and a number of others have been providing some support for operators in the TensorFlow Lite frontend. And we'd like to thank all the reviewers who've been reviewing and helping us get started and working in TVM. We are looking at various differences that we see with respect to versions of the frameworks. Different versions of the frameworks have different or levels of architecture support. While working on TVM, one of the things we've noticed is that there aren't many easy debug tools available. So one of the things that one of my team members, Leo, did was to write a whole set of LLDB pretty printers that have now been merged into upstream. So please try and use them. They'll hopefully help you a little bit when you're debugging your relay IR nodes and provide you a simple printing interface in your favorite debugger of choice. And we are also investigating micro TVM, which we find interesting for a lot of our Cortex-M devices. In terms of Ethos NPU, we are working internally on the graph partitioning for the NPU, and therefore we find a lot of the work that's happening with bring your own code gen to TVM quite interesting. we would also like to improve that further, because it's not necessary that everything that every relay IR node will have a 1:1 mapping with the code generator. So we may want to think of improving that as we go further. And we are integrating support for Ethos, for the Ethos family of NPUs. In the future, over the next year, we see these are the areas that we are interested in working on, and we would like to work with anybody and everybody in the community in terms of these areas. The areas are really around graph partitioning and relay optimizations. We would like to pick up more on that. We would like to improve code generation for our CPUs and essentially use more of the instructions that are available on the CPUs through TVM. We'd like to improve the way in which auto-tuning is done and figure out ways by which we can deploy auto-tuning on the auto-tuned schedules in a sensible manner rather than relying on just top hub to be available. A lot of our users might be sensitive about having an access to an external network while running their inference compilation. So we would like to try and improve that side of things as well. A lot of us who are probably using TVM as ahead of time compilation have got our own set of command line utilities and tools for using TVM. We would like to try and see if we can standardize that across the community and provide something like a Clang or a GCC driver to TVM so that people can use that efficiently. We think that's a good thing to do because it means that the barrier of entry to TVM can be reduced further. And at the end, we are also very interested in micro TVM and pushing that further. Speaking a little bit about architecture support, in terms of the V8A architecture, we've got the scalable vector extensions, which is the next generation of ARM's vector instruction set. This is quite different from a lot of other vector instruction sets because the concept of a vector length is not embedded in the instruction set. You've got a vector length agnostic instruction set, and that should be interesting to look at. We're also adding new instructions to support matrix multiplication. This was announced recently as part of our 8.6 instruction set. We're adding support for bfloat 16, but at the end of the day, a lot of our devices do run with advanced SIMD, which was introduced in V8, and we would like to improve support for that in TVM. In terms of GPU support, a lot of our work for GPU support is going to be feedback driven. So we would like to see how to improve support for Mali Bifrost, which is sort of the last generation of Mali GPUs, and move on to Mali Valhall, which is the latest generation of Mali GPUs. And finally, in terms of the microcontroller space, there are a number of instructions in the microcontrollers which are capable of doing SIMD-like operations on the integer register set. We think they are particularly relevant for a lot of ML workloads. We would like to see how best to use them directly from TVM. Those would be interesting areas. And we would like to see how best to support our vector instruction set that we've recently added into the M profile. This is what we call helium or MVE. These are sort of the areas that we want to look at over the coming year. I'm not going to stand here and give you exact timelines because I don't know them. We'll have to work it out as we go along, depending on priorities for the project. But this is sort of what we see the possibilities with TVM and the ARM architecture in general. In terms of challenges and opportunities, some of the things that we've seen, I think a few people have touched on this. Wouldn't it be great if we could do pip install TVM? The single biggest problem I have with a new starter in my group is getting them started to build TVM and figure out all the different combinations of CMake and figure out what is the correct thing to do. There is a lot of confusion out there. If we can simplify that for our users, I think we'd be doing ourselves a whole load of good. I know other speakers have said this already, but, so I'm just going to reiterate the point and say, I'm with you. A lot of us are looking to ship products and looking to ship SDKs or other things with TVM. If we are to do that, we could sort of share in some of the efforts in terms of doing a release process and sort of think about going up. There's a lot of good technology that we've got inside the TVM stack. How best can we get this to our users? How do we make this easy for our users? And how do we collaborate so that we're not duplicating effort between all of us? All of us have to do this mundane stuff. It's bread and butter, but it would be nice to do that collaboratively. In terms of the other side of things that I wanted to touch on, continuous integration is a topic that keeps coming up internally. It would be nice to be able to have a common framework for running our execution tests and to be able to test on all of the targets that we support. At the minute, the CI tests on particular architectures. I'd like to extend that to support more of the target backends that TVM supports. We should also start thinking about what it means to manage version updates and frameworks. I've got a list of 30 operators in TF Lite that my users are going to want to use. How are we going to move forward from TF 1.13? Can we make a process for that? Can we look to see what that looks like, and how do we move forward from there? The TensorFlow was just an example. I'm sure we're going to have the same question asked of us with all the other frameworks as well. In terms of scalability, one of the things we've noticed is we've probably got to start thinking more about a development practice, trying to isolate features versus bug fixes. All of us are busy. We have our own amounts. We have our own constraints. But it would be nice if we could distinguish features versus bug fixes. This means that later, when we have to start worrying about releases, cherry-picking patches and dealing with that becomes much easier, rather than having to rewrite history when we have to merge things in. These are all things, and these are all parts of growing up, but we've got to grow up over time. Developer efficiency would benefit. TVM is moving extremely fast. The number of posts, the number of pull requests are pretty high. It's very hard to keep up with what's going on. It would be really nice if there were better explanation with changes. It would be really nice if we had debug helpers, if we paid attention to some of these things. And it would be really nice if we could understand how the test infrastructure works. We have always got a challenge and a trade-off between making sure that our current pool of developers have an efficient experience with what they're doing, but also we have to keep an eye out for the new developers that are coming to join us. How can we make their life easy and do things? And with that, I'm going to stop and say, like everyone else, we are hiring, not just in the TVM team, but across ARM, across the whole set of things that we do with machine learning. And I'd like to stop there and take any questions.
Hi, thanks for the talk. So regarding the LDB pretty printers, can you tell me a little more about how I would use them and where the code is actually upstreamed, if it's in the LLVM project now?
It's not in the LLVM project now. It is in the TVM project.
Okay.
LLDB provides a Python interface, and you're able to write a whole set of Python helper functions that you can use. It was actually merged yesterday or day before. I can dig it out and send you a link afterwards.
That would be great, thanks. Just to clarify, so you've committed these extensions as Python scripts in the TVM repo? Okay, thank you.
There and there.
Other questions for the audience?
Hi. Yeah, you had a picture early on of where you had TVM next to ARM in it.
Yep.
And I was wondering if you could expand upon what the differences are that you're supporting in those two.
So ARM-NN for us is really a sort of NN-style API software stack. We are using TVM as an ahead-of-time compiler stack. The two of them are different in terms of what they're capable of and what they're doing. That's sort of what it is. It's very hard to draw a block diagram that captures everything that you want to do on a 2D plane. So that's sort of what.
Yeah, I guess, you know, because they're both taking in an ML framework and they're both producing an NPU input.
They're not producing an NPU. They are structured over the NPU compiler. As I said, it's really hard to draw 20 different boxes to make this fit.
Right. Well, that's good. Thanks.
Any other questions? So just one last question. You mentioned better command line utilities.
Yeah.
And packaging TVM as a more GCC-like compiler, perhaps?
No, not really GCC-like, Clang-like as well.
Clang-like, yeah. And so what would be the input to that compiler?
Really good question. And the input would be a model.
So a serialized model.
A serialized model, take that in TF-Lite, PyTorch.
Relay, maybe?
Relay, maybe, if we had some sort of an input for that. And we were able to create those relay graphs, then why not? But essentially, that's a very rough sketch of what we think it would look like.
Yeah. All right. Great. Well, I really appreciate all those insights. Let's thank Ramana once more.
PDF's there, so just load the PDF from there.
1 second. We have Elliot from Xilinx. He's a distinguished engineer, has been working in a team that bridges the gap between a multitude of frameworks and a multitude of FPGA-based accelerators, and is going to talk about the adoption within his group of NNVM and Relay and their experiences in using the TVM stack to target Xilinx-based accelerators.
All right, great. Okay, thanks, Thierry. Yeah, so as you know, Thierry mentioned, we work in basically taking machine learning models and mapping them onto the FPGA. And it's been a great set of talks so far because, you know, we're all kind of addressing the same challenges. How do you go from a model to the accelerator itself? And so normally, you know, FPGAs, you've known FPGAs as being hard to use. So there's a long history of FPGAs as being a niche product. If you had to use FPGAs, you'd be sitting in the lab in front of oscilloscopes or looking at waveforms or, you know, having to design your own PC board. And lots has changed in the last 10 years, and especially the last 5 years in particular. So for example, you can go to Dell, you can actually buy a server with PCIe cards that have FPGAs inside them. You go to Amazon Cloud or Azure, and you get FPGA instances in your cloud. You know, same thing with Alibaba, Huawei, Tencent, they all have FPGAs in the cloud now. We have these boards, for example, you know, ZCU 104, Ultra 96. These are basically FPGAs with ARM cores on them. And one of my colleagues here is actually from Ireland. He can actually SSH to his desk in Ireland and run his work on one of these boards because it's all just, you know, an ARM processor plus FPGA now. It's very easy to use these. And our goal really is to take machine learning models like you see here, the typical CNNs, and allow our data scientist customers to then use the FPGAs more easily to run these kind of models. And FPGAs are showing up in a lot of places you wouldn't normally expect to see them. So I was giving a talk at MIT last year, and the day before my talk, this popped up on Twitter. So, you know, as you see, Jan LeCun, we all know who he is. And at one point, he mentions he was a chip designer. He actually wasn't just a chip designer. He was actually an FPGA designer. So, you know, FPGAs have had a long history in helping to accelerate machine learning applications. A lot of them have been, you know, in the research area, trying to experiment with new architectures. And over that time, you know, we have from, you know, the 2009, 2010, 2011, even before AlexNet, these were being used for accelerating machine learning. The diagram there is actually a 3x3 conv2D, and the data flow in a systolic array on one of Xiaoyong's FPGAs. So now, more recently, you know, I'll explain a couple of different architecture types for recent styles of architecture we've been seeing on FPGAs. So one style is what I'd call a synchronous data flow, in which basically the entire model is laid out physically in memory and on the FPGA. So if you think about it, you know, if you're thinking of let's say, for loop, this would be the equivalent of unrolling a for loop. So you actually have individual parts of the FPGA dedicated to each layer in your network. So there are some limitations with this. Of course, you can only fit so much on your FPGA. But once you're able to do this, it's very, very efficient because you don't have to move data between memory and the FPGA. You could stay within the FPGA itself. Another style that's very common is more a matrix of processing elements. So a gem core basically inside your FPGA. And you generate instructions for that gem core, so there's usually an instruction set. And you cycle data through from memory on the chip or maybe external memory through the gem array and back to memory. So these are kind of two different approaches. We see a lot of different architectures. But I'm going to highlight a few architectures based on these two key concepts. And I'll explain how TVM will really help with these kind of problems that the architectures have. So first, on the left-hand side are the kind of unrolled loop style architectures. So some interesting ones here, HLS4ML. There's actually some work from a few MIT professors in collaboration with CERN and Fermilab. What they're actually doing here is using machine learning at the Large Hadron Collider in Switzerland to analyze particle collisions. So what's happening is at the LHC, I think every 25 nanoseconds, there's a particle collision. And they're actually creating a machine learning model using Vivado HLS and Xiaoyong's FPGAs to analyze these. And so we've been talking about, you know, latencies in the millisecond range. These guys are running inference every 50 nanoseconds. So it's a huge order of, you know, magnitude difference in what they're able to achieve. But this is only because they're able to essentially unroll the loop in the FPGA and run it without having to go to external memory. There's some other projects. The Feng project from Xiaoyong's Research Labs is more for very low bit width. And, you know, in that case also, it's really designed to instantiate a specific network, but to do it very efficiently. Recently, Alibaba also presented some work at Hot Chips 30 last year, which also was a kind of on Xiaoyong's FPGAs, it was a dedicated ResNet 18 accelerator. So there's one style of approach, you know, on the kind of unrolled loop style, I would call that. And then at Xilinx, we have a couple different accelerators we built. One of them is called XDNN v3. It's more for the cloud applications. Now, there's a very large systolic array that we build for this. So, you know, we have data that either exists on the DDR, and we pipe it through the gem array and then back to DDR, or we buffer some of it in internal memory. We also have another architecture called DPU v2, and that's more for our edge devices. So it's designed to be more scalable. Still has an instruction set, still has very small gem cores, but, you know, we just send data from DDR through this core and then back. And then, of course, there's the TVM Vita architecture, which also has a systolic array. There's a gem core within it. And again, you have an instruction set. It actually has some characteristics of the kind of left-hand side, where you can tune the model for specific models, for specific networks. But it still has a core block, which does all the computation. Now, what's interesting about all of these is every one of these groups, these 6 different architectures, they've written their own TensorFlow parsers. They've all written their own IRs, right? So that HLS4ML project, these physicists at MIT, they're actually spending their time writing parsers for TensorFlow instead of analyzing, you know, the particle physics experiments. So this is where one of the first things we see that TVM actually can be very useful for all of us. as the front end, as the IR that all of us use. Now, even at Xilinx, those three architectures, they actually have 3 different front ends. So Xilinx Research Lab, they started with the front end for DarkNet and kind of expanded from DarkNet to Caffe and then to TensorFlow. We built the XDNet v3 TensorFlow parser in my group. The DPU v2 parser came in from an acquisition. And so, there's a lot of overlapping work that we want to merge together. So that's one aspect of it, the front-end compilers, the front-end parsing. Another aspect that's in common for all of these is that they optimize a certain part of your network, but not everything, right? All these approaches, they can certainly optimize conf2d, maxpool, and many of the operations that are very common. But there are always going to be some nodes or some operations that are not supported by these. So even though FPGAs can be reconfigured in milliseconds, it still takes time to actually build that core that you want to use in your FPGA. So this is where then we use another aspect of TVM, which is if there's a node which we cannot handle, we want to fall back to a CPU implementation. So these are kind of 2 areas that we're actually using TVM today to basically help on the front end in the parsing and also on the back end for the CPU code when we can't handle it in our normal accelerators. So the typical inference flow, the kind of compilation tool flow that we have, it's pretty standard. We start off with our own compilers. So this is, again, before TVM enters the picture. So we had our own compilers or parsers for TensorFlow, Caffe, MXNet, and Keras. And from that, we had our own IR representation. From that, we would do our compilation steps, our quantization directly from that. And from there, we'd go to the runtime environment. In the runtime, of course, we can call the FPGA for the FPGA layers. But it used to be that if there was a CPU layer that we didn't support, the user themselves would have to write it. Either write it in C++ or Python, or have some way of calling it, because we just didn't have a way of generating that code. So now, as TVM enters the picture, we brought in TVM in the front end, so we can use TVM's parsing and relay graphs and NVM as well. And in the back end, for the runtime environments, we're able to take the TVM code generation for CPU and merge it with the work we do for our FPGA compilations. So this kind of, the big picture is we are using parts of TVM, but not all of TVM. So, in the future, we'll start looking at more use cases of TVM in Xilinx. But I think what we've seen so far is that this is going to be very valuable to all of us, not just, within Xilinx, but those architectures that I showed earlier. I think everyone will benefit, from the uses of TVM. So for the actual work, the way it works internally is that, so we started off initially earlier this year with NNVM, and then we moved to Relay. And the basic idea is that from Relay and NNVM, we convert to our internal Xilinx IR representation, which we call XF graph. And from that, we call our compiler and our quantizer and our partitioner to see what's going to be for the FPGA and what's going to be remaining on the CPU. So from the partitioner, we basically, send information back to the relay graph saying this is what we're going to handle in the FPGA. Then everything else would just stay as a normal relay node and goes through the normal flow of relay. Now the compiler in this case is still our pre-existing compiler. So we had, built this over a number of years. And as you all know, it's quite difficult, quite an investment to build compilers. So in this case, we're still using our existing compiler in the subgraph. But in the future, we might start looking into auto-scheduling and some other opportunities in TVM. And so, you might ask, why don't we just use relay as the IR directly? And so, we like TVM and we use TVM. But as a company, Xilinx has to kind of fit in a lot of different areas. So at Microsoft, there's Onyx Runtime, which is kind of similar to ARM NN, where it allows for Onyx models to come in. There's a concept of subgraphs and plugins. And so, we have to fit into that as well. There's also ARM-NN, which is a similar kind of structure. Because of course we're partners with ARM, we have to fit our compilers and IPs into ARM as well, the ARM infrastructure. And then there is, other, Alibaba has MNN. Similar story. I think MNN is more similar to TVM than ARM-NN and Onyx are. But again, we work closely with Alibaba, as well as MLIR. So there's a lot of kind of requirements from Xilinx to fit into different areas. So that's why currently we haven't ported our code directly to Relay. But in the future, we'll look for our next version of compilers, and whether that uses Relay directly, I think we'll have to see how that goes. So generally, when we see graphs, we kind of handle it as a pre-processing phase, the core computational phase, and then post-processing phase. And the pre-processing could be either in the FPGA or CPU. For example, array size operation could easily be accelerated by an FPGA, or it could just sit on the CPU. And then within the actual core computation, you would have subgraphs and potentially unsupported layers. You know, if somebody's writing a brand new network type, they have some layer that we just haven't put into the FPGA yet. Of course, there'll be some unsupported node in there. And finally, there might be cases where we can take the model and parallelize some of it. So create multiple subgraphs and either run them on 2 FPGAs or even use, we have multiple cores in the FPGA typically, so we can take the FPGA and actually run part of it on one core and part of it on another core. And of course, the post-processing, same story, you know, NMS, for example. We could put NMS on the FPGA as a core or just allow the CPUs to be running them. So as we go through our flow, you know, we take these graphs and we modify the relay graph such that that subgraph that we originally had, which was a number of nodes in a relay, they now get combined into a single node in the relay graph. So in this case, we would have basically 3 FPGA nodes. Each of them has calls our own compiler to generate the right, you know, code for the FPGA, but they're all integrated into the same relay graph. So if I want to run this through TVM, TVM starts at the beginning, sees the FPGA node, calls the FPGA, comes back to TVM, and kind of continues the process through that way. So the output actually looks like what you see on the screen. So the output from TVM for the CPU are basically the lines at the bottom. So of course the graph, the TVM graph in JSON, the parameters, which are the weights for the CPU portion of the graph, and the .so, which are the CPU, you know, code gen. For the FPGA, now we have, this is for one version of the FPGA architecture. So we have the compiler instructions written out in JSON. We have the quantizer scaling information also written in JSON. And then the weights for the layers are actually written in HDF5 format. So when we go through, we basically load these into DDR of the PCIe card or on the you know, ARM card that we have or board. And then as the network runs, we basically execute these as, you know, TVM sees them in the graph. So this is an example of, if you looked at that JSON file from the TVM output, this is what you would basically see. So there's a node that we've registered in TVM, which we just call in this case Excel fused. So it's a, you know, massive fusion of all these nodes in the graph. And from that, you know, once TVM sees this as it's executing, it'll then call our registered function. Now we wrote this in Python, and the main reason is we write a lot of these kind of applications with a plugin in Python because it makes it easier. We don't have to recompile TVM. We did this actually for TensorFlow and Caffe as well because they have, you know, PyFuncs in TensorFlow and Python nodes in Caffe. Of course, PyTorch is, you know, Python. But these nodes are actually very useful because from kind of the end user perspective, they can take just a Docker container with a pre-built TVM image, call some Python APIs to register the function, and the function just uses our Python APIs to call the underlying architecture inside the FPGA. So there's one kind of missing part here. So, you know, what I described works very well, and we're getting good performance, and we're actually, we submitted a PR. So we're working with SageMaker Neo team. We submitted a PR to their fork of TVM, and eventually you'll kind of, you know, figure out how to merge all these ideas together. But there's one missing piece that hasn't really been described yet, but we do see it kind of as a limitation in our system performance. That is, for some of our devices, they're quite complex internally. So for example, the Xilinx ZU7 EV, so it has an FPGA inside. It also has a Cortex A53. It also has a Cortex R5 and the Mali GPU as well. So, you know, we want to use all of these, not just the FPGA part, or not just, you know, the CPU plus FPGA. We want to be able to actually use the entire device. So this is something we're trying to look into. You know, how do we create pipelines within the device itself, have both, you know, the CPU plus GPU and FPGA all working in parallel. So outside of this, we're able to create these in our own cloud devices. So if we use our own APIs, we typically do pre-processing on one CPU thread, then we could send it through to the FPGA thread that's actually calling the FPGA. Then we could do post-processing on some other CPU thread. But when we go through the TVM runtime, we're not yet able to actually run all these in kind of a streaming fashion. So I think we might be looking to that, maybe some prototypes. And if any of you are also seeing this kind of issue or maybe want to discuss it, we're certainly open to collaborating on this idea. With that, most of this work was actually done by Joran, who's here from Ireland, and Hassan, who wasn't able to make it. But they've been doing great work with Relay and NVM, and it's been really impressive what they've been able to achieve. And so if you have any questions, you can contact me. I'm just Elliot@xilinx.com. With that, thank you.
All right, so we have time for a few questions from the audience.
That was great. Thank you, Alex.
Sure.
So I was curious if you could comment a little bit on how you see using frameworks like TVM to map to emerging reconfigurable hardware, like Everest, for example, has like coarser, DSP blocks that can do richer ops, and that seems like something that in general has been challenging for compilers, right, to make use of more complex functions. But if it's specialized, it must be easier. I'm just curious if you guys think
actually, I think the new architecture, which is called Versal, it has these special engines, which are vector operations and things. I actually think TVM has the most potential in Versal. Because for our pre-existing devices, you kind of have to write RTL or HLS. You have to kind of make these structures. And the instruction set's typically not easy to modify. But so the Versal devices are much more easy now. It's more like a standard core, So I think TVM has a lot of potential in that area. And that's kind of the next thing that I'll be looking at. So next year, 2020, so we'll really start looking into Versal devices.
You had shown a slide where if the graph is not fitting on one FPGA, it will be split on multiple FPGAs. Mm-hmm. So I'm wondering, what kind of infrastructure exists when you want to run the same network on multiple FPGAs?
So some of that work, we've done some very basic experiments, but haven't fully fleshed out how it's going to be implemented. We have some architectures where we've kind of been experimenting with it. And typically, these are communicating through the CPU itself. So it's, from the FPGA PCIe board to the CPU and then to the other FPGA board. So it's not efficient at all. It's more proof of concept. We do have some ways of actually communicating from one FPGA to another. There's certain standards that are used in other application domains for FPGAs where you can stream data from one FPGA directly into the other. Well, we haven't actually explored those yet for machine learning. I think that might be something we start looking into in the future.
Thank you.
One more question. With the set of FPGA designs that you presented in that one slide, how many of them are open sourced, or how many of them do you want to open source?
Sure. So, the first two, HLS4ML, is open source on GitHub. Just search HLS4ML, you'll find it right away. The Feng project also is open source on GitHub. The third project is Alibaba's own work, and I'm not aware that it's available anywhere other than a poster with the results here.
Just corner them here,
Yeah. Well, we actually used to work together at Xiaoyong, so. The two Xiaoyong cores, XDN V2 and XDN V3 and DP V2, those are not open source, and there's no current plans to open source them. They're more production right now.
Yeah.
But so, for example, DPU V3 is coming out soon. So maybe in the future, V2 might be open source, but I'm not sure. No discussion at this point.
Okay. Great. If there's no more questions, let's thank Elliot.